Okay, so my name is Ralph Buyman. I'm from the University of Luxembourg, and I've spent I think the last 8 or 10 months basically looking into security of cell phones. I'll start with basics, like what a modern smartphone looks like, because that's the target that I've chosen. I will talk about a topic that has been neglected thus far in this area, namely baseband security, or rather baseband insecurity. I'll tell you how to find bugs, how I found bugs. This may work or may not work for you in this software. I'll talk about the practicality of exploitation and what this implies for everyone who has any connection to mobile phones. And I'll give an overview of the current status of disclosures and where we're headed in the next couple of years, I think. Okay, so let's start. While I'm talking, I'll try to build up the demo setup as well. So because I have a demo for the vulnerability that was recently fixed by Apple this week, which was a heap overflow in the baseband that I reported. Because my USRP was slightly broken apparently in the last couple of weeks already, but it has reappeared, this problem. I had to switch to a different USRP, so this means I can't attack the shiny new iPhone 4 for clocking problems, can only do the old one because the clock stability doesn't allow me to do that. It doesn't lock onto the carrier of this particular USRP. Okay, let's have a look at a typical setup where I've abstracted everything away for you that is not necessary in this talk. So what we'll be talking about here is we'll be mostly talking about this base transceiver station, which is under our control because we carry it around, and about the mobile station, which will be attacked by us. This is like the typical scenario you have in a cell phone network as well, but you have all of this back-end stuff there as well, which is like the base controllers, the base station controllers, the HLRs and the VLRs and links to that. We don't care about that because for now we're trying to be a rogue base station and we're impersonating an operator. So the interface between the base transceiver station and the mobile station is called the interface, or in lay speak, the air interface. So when you have a look at this interface, you'll see in most of the literature that it is composed of 3 layers. Layer 1 to 3, they are called simply. It's not the standard OSI, it's somewhat different. So in layer 1, you have the physical layer, which is basically how things are transmitted over the air. This is usually done by a DSP in the smartphone, decoding and encoding into this. Then you have the layer 2, which is basically derived from the ISDN LAPD, LAPD protocol, but in this case it's the LAPD mobile protocol, so they have a couple of additions and some things were removed. I mean, for instance, in ISDN, you don't have collisions on a channel. This doesn't happen. Well, it might happen on an air interface. And this layer 3 is what we will concern ourselves mostly with because this is where the interesting stuff happens, as we'll see later. And this can be subdivided into 3 other layers, namely the radio resource, the mobility management, and the connection management. So maybe I should answer the question first, why smartphones? I mean, there are many other phones. I mean, okay, different question. How many of you have a smartphone in this room? Okay, now, don't be ashamed. How many of you have used a regular feature phone, like dumb phone? Okay. Okay. So, yeah, so as you see here, like the feature phones were somewhat in the minority. And this is because of several things. So first of all, I think because this is like a kind of technical audience, so it's more likely that you guys have smartphones. Also because you're sitting in this talk. That's skewing the bias here. But basically, in the late 20th century, what we saw was that these little devices called personal digital assistants, they merged with cellular phones, and this is what became the smartphone. Now, there may be many, many more feature phones than smartphones, but usually attacking the guys or girls who carry the smartphones makes for much better value. Because, I mean, what do you want with a phone that has like $5 of credit? I mean, that's ridiculous. And the conversations that you will listen to if you tap that are probably pretty boring as well most of the time. So that's why I chose, that was one of the first reasons why I chose smartphones. But the other reason is there's less variety as well. Like with feature phones, like you have a huge variety both in the firmwares and in the models. So smartphones basically have driven PDAs into extinction. How many of you still have a regular PDA that they use? Okay. Okay. You have a calculator as well, right? Okay, abacus. Okay. And the interesting thing is that I didn't know this 2 years ago, that smartphones are a multi-CPU architecture. So there are at least 2 CPUs in most of these smartphones, namely an application processor and a baseband processor. And in 99% of all cases, ARM CPUs are used for both. The exception here is Freescale. So there are CPUs by Freescale which are ARM-less, so not legless, ARM-less, no. They just operate layer 1 to 3 on a DSP. And the trend is that the designs are going to a single chip solution, so the application and the baseband processor are merged into a single package. Now this is interesting for several reasons, because here you see the 2 dominant smartphone architectures. So the left-hand side is what's used in iPhones and in other, like I think in the Samsung Galaxy i9000 as well. And but this is like the more costly solution because you have a separate CPU for the application and separate for the baseband processor. Now they talk to different RAMs as well, so you have another component that you have to duplicate, and then you have like shared memory or sometimes serial communication over some GPIO lanes between the 2. The other side is what you see in most of the Android phones that are based on Qualcomm chipsets, namely that you have an application processor and a digital baseband processor that, for cost reasons, access the same RAM. Now, back in the days, like 10, 15 years ago, carriers thought, well, the users shouldn't like really get to mess with this radio layer, right? So this is why historically the baseband processor in this design becomes the master. This is apparently changing at the moment because of oops, new email, because of these recent results. But at the moment, everything I've seen where this architecture on the right-hand side was employed had the baseband as a master. But now here's a problem. When I spoke to this anonymous engineer, I will call him for now, 2 years ago, who told me about this multi-CPU architecture, I suddenly realized nobody had looked at this at the baseband side and found, like, I hadn't seen any published vulnerabilities in that yet, and I knew several people who were doing reversing of these firmwares, and I knew several people who were pretty good at security, and none of them had heard about it, had heard about security vulnerabilities there. And then I forgot about it, and well, this year I started looking at it again. But before you do something like this, you got to do some market research, right? So you got to know who you attack. So the market research I did last year was, I'm not sure how good this is. So these were the shipment shares for the third quarter of 2009. So this is like the overall shipment share. This is not for smartphones. This is for all of the phones. And you see that Qualcomm and MediaTek are the two big players together with Texas Instruments. And ST Ericsson and Infineon are good as well. Now, as I said before, I care about smartphones, so I looked at what is dominant in smartphones, and it was like Qualcomm and Infineon, because like Infineon is all of the iPhones, and Qualcomm is in all of basically all of the HTC phones, and like most of the Androids are Qualcomm based. I later looked at MediaTek as well. I will not talk about this in this talk, but it's actually much like, from what I found, it was worse. I haven't finished that part yet. So let's talk about security of the software. So it turns out that the code base for these things was created in the 90s. I mean, that's kind of obvious because that's like when was the standard written in the late 80s. So, but the problem is like it also this 90-90 attitudes towards security is permeated in the code. And there are fundamental flaws in how people treat inputs that comes in over the air interface, because it's trusted, right? I mean, if somebody has a damn base transceiver station, he must have had a lot of money, and hence, yeah, we should trust him. So it apparently didn't occur to the people at the time that one day people would be able to buy or build base stations on a chip for this technology. So I mean, yeah, 10, 15 years ago, you'd have to spend a substantial amount of money to build your own BTS. And I think at the moment, the cheapest that you could buy is like the cheapest commercial one that you could buy that is not like a nano BTS is like a Huawei for, I've heard figures around 50,000 for carriers, US dollars. But as we'll see later, there are other options that you've probably seen here already. Now the problem is if you trust these things that come in over the air, there are many, many length fields because these guys apparently were greatly inspired by ASN1. And there are almost no exploit mitigations. I say almost because this thing here in the baseband has one. There may be others. But as I said, I've just looked at, this talk is just about Qualcomm and Infineon firmwares for now. And like in the iPhone 4, they have enabled DEP on the baseband CPU. How they did that is kind of funny as well because it's not really an ARM feature that they use, but it's like a crossbar that's like in front of the CPU core and not in the actual CPU core. And you can only, like this is enabled at boot time and you cannot reset it once the CPU is running until the next reset signal comes. But there are ways around this. So you probably forgot what the stack looks like, but this is important, so we'll have a look at it again. So this was a stack, and now we'll have a look at where we should dig deeper. So when you look at the standards, you realize, well, I think there's not much in layer 1 that you can really do. Layer 2 messages are too short. You can crash a couple of things there, but you want to have like a payload to do malicious things as well. So we go layer up, and we look at layer 3. And this is specified in GSM 408. And here you have variable length messages. Great. So they can be either tagged or non-tagged. And you have a maximum length of 255 5 bytes because they encode that in 1 octet the length. However, they also use real ASN1. I mean, this is like this TLV format is like you see people have done too much ASN1 and had too much, well, I'm not sure how to phrase this politely, but too much brain damage has been done by ASN1 to these people who designed this. But there's plenty ASN1 as well. For instance, for this RLLP, which Harald demonstrated in one of his talks at the Congress. No, sorry, this was at HAR, right? Where you demonstrated for the first time that this can be used for querying the location. Yes, sorry. And in some of the stacks, you find problems with parsing these messages as well. And it turns out that the GPRS layer is very, very fruitful. But for me, there's a problem here because I can't speak the GPRS layer yet with the OpenBTS because it needs a different layer 1. So the layer 1 implementation is somewhat different. And according to people who have written OpenBTS, this is like 1 man-year of effort to write this for GPRS. Okay, so this is where things got interesting, and these were my initial targets. So I started with a stack of iPhones and an HTC Dream, because that's just what was current at the time for me in terms of cell phones. And I started with what most people do. Actually, like at the time, fuzzing was a big thing. So people told me, "Hey, you can totally chill and find bugs at the same time." Turns out this is not true with baseband firmwares because, well, they just crash and you don't get any information, any easy information usually. So you have problems to triage the crashes. You have lots of crashes, but you don't know which ones are basically the same. And it's kind of like stumbling through a back alley blind. So the alternative, of course, is to do static analysis. But the problem is, well, there's no source code publicly available. But a couple of years ago, there was a phone called Vitel TSM30 by an Italian company that went belly up. And the source code for this at some point appeared on the SourceForge page for a number of years and was downloaded by many, many people. And if you ask around, you probably can get a copy of this still. And this is very useful to find out what the general, what the general architecture of these things is. Because before that, I didn't have a clue. I mean, I had some ideas what people could potentially do, but these were solidified by looking at the source and refuted in some other cases. So the conclusion was like, okay, we have to reverse binaries here. That's okay, I like reversing, so how do we start? Most of the firmware updates that you download for smartphones already contain baseband firmware as well, because the smartphone vendor, at the same time that he patches things in the operating system, patches a couple of things here and there in the radio stack. But they usually are packed multiple times, and you need to figure out how to extract them. So for the iPhone, there are tools to do that because people have invested a lot of effort into unlocking these phones. And similarly for HTC phones, there's this community called XDA developers, and they know all about ripping apart and building new Windows mobile images. And some of that transfers over to Android as well. But you find that the Qualcomm firmwares that you usually find in a radio image for an Android, they're usually just ELF files with the loader in front of it. And you can, if you know the right offsets, you can straightly load this into IDA, and you have a good starting point. Sometimes even people leave symbols in these, which is very nice. For Infineon, you need a custom loader and relocator. This is somewhat yucky. It's easier on the first generation things because there's lots of information available. on the iPhone 4, you have to really read what's it called? I think ebl.fls to see how relocation is done if you want to do this statically. But the other thing that you can do is people use all of these bugs to unlock the phones, to do soft unlocks these days. And you can use the same path to inject your own code into the baseband through a bug in the AT command parser. And hence, you can gain information about the MMU configuration, for instance, or you can dump regions of memory. This is very nice, but probably shouldn't start with that initially. It's nice when you get stuck later. Okay, now you have like this huge binary at the right address in your IDA, but you still don't know what's what, right? So there's this company in Bochum that is run by Halve Flake. They make a great tool called BinDiff, and this can be used for symbol porting. So what you can do is you start out with a guess of what compiler was used, and you take the runtime of that compiler, and then you load that into IDA, and then you take the image of the firmware image of the phone that you're looking at, and then you say, okay, port symbols, and it gives you an indication of how, by looking at the call graph, how similar the call graph for certain functions is. And if you like have a 99% match, well, that's probably the same thing. You look at the assembly again, and you verify this for, and then you figure out, for instance, where mem copy is, or where string copy is, or SPRNF, or all of these things. And then you have something to go on, so you can go from the inside to the outside of the functions. Also, you can, if you have a BinNavi license, you can identify functions that do memory transfer. Not now. Sorry. You can identify functions that do memory transfers by looking at the intermediate. They have like an intermediate language called Rail, and for this, there are analysis tools that can output you all of the functions that actually do memory-to-memory transfers. But it gets better because when you look at these firmwares, you see there are a lot of strings there, and for some reason, some of them have they have source file names in them, and then you look at where they're referenced from, and then you realize, oh, it's an assertion because somebody ran into an error case, and he now wants to log an assertion in the debug, but this went into production. The other thing is, oftentimes you have very clean-cut regions in the firmware for different things. So for instance, that hex 1000 to hex 5000 is the RR layer. So this is much too small, but then you have another region adjacent to that, which is the mobility management, and then somewhere else is the AT command parser. So it's not all over, but once you have identified one function of a certain type, you can be sure that there's similar functionality in the same region. And one tool that I've only recently come to value because I didn't have access to it because I thought it was too expensive, was the ARM decompiler. But boy, it's worth the money. I mean, if you do this for real, you should invest into that because it saves you. Unless you pay $5 an hour, that's the way to go because you get a quick overview of what functions do very quickly, and I can show you one of these if either is open somewhere. This shouldn't be a product demo for ILFAC or something. But so this is the nucleus error handler in the iPhone. I think this is yeah. So the iPhone 2G is this. So the other thing is don't get too ambitious. Don't start with the biggest firmware you can find. This is the smallest one, and you can usually port the results to the newer ones. So here you see an error handler that is basically used all over the place. I don't see how many times, but okay, you kind of get the impression. And then you see all of these nice switch statements, which you can read. I mean, you can read the same in assembly as well. But it gets kind of painful. And with when you do this with BinNavi, you need a really big screen to see the graph correctly. Not sure what I can see. I think the screen is too small here to do this. Now switch back to Keynote. Okay. Okay, so that's the first step. But then you figure out, wait, this all looks like very much independent of each other. And then you see, oh, it's just different tasks that communicate with each other because they run a real-time operating systems, and different parts of the stack are different tasks usually. So you have the problem that you need to identify these different tasks, and again, the assertions and logging functions are very helpful. So after several bugs were found, I went back to the standards and looked for more. So what kind of bugs can you find in these things at the moment? There are many, many unchecked memory copies, and these are easily found once you've identified a mem copy. There are lots of structure or object. I'm not sure whether it's a structure or an object. I think it's actually a structure because I haven't seen much C++ in these things. Issues where things are, basically GSM has a lot of state machines, right? So in some of those, you can actually jump into states that are not meant, like you can arrive in a state that you're not meant to be in, and hence a function will access a structure that has not been properly initialized or that has been deallocated already. So this is great fun as well, but it's somewhat more difficult to exploit than the first kind. So this is like to use after freeze uninitialized variables on the stack. And well, I mean, infinite loops are kind of pointless, but yeah. The other thing the other interesting thing that it can lead to is it can lead to info leaks. So you can sometimes get portions of the memory read out over the air that way. This can be interesting when you try to fingerprint stacks, or when you want to like read out certain regions of memory because you want to have a cross phone exploit that works on, say, all phones that have a certain stack. There are protocol, I call them protocol foobars. So these are basically code paths that should be only for, well, that was my initial understanding, but maybe I'm wrong here. Code paths that are only for UMTS or CDMA, but that can be triggered using GSM frames as well. I've later been told that this is for compatibility reasons. This is yet to clarify. And one of these examples I'll give on one of the next slides. I'll start with one bug that is fixed now, that was fixed this week in the iOS 4.2.1 firmware. So there's this TIMSI reallocation. TIMSI is a temporary mobile subscriber identity. Now this is for pseudonymity, basically. So you have the IMSI, which basically ties your SIM card to your identity. I think we had a philosophical discussion about that yesterday. And then they wanted to be able to disguise from attackers who cannot decrypt, or who don't have the capabilities that Karsten has, who's really registering when he goes through different cells. So initially, of course, you have to have an exchange with the IMSI, but when you then roam through, like walk through the different cells, shouldn't be able to trace that person unless you're the operator or law enforcement agency. So they use this TIMSI. This is like a 32-bit value, always, always, always. But for some reason, they they have prepended a length field to that. I don't know why. And it turns out that some people actually look at that length field and say, hey, yeah, sure, we should trust that and copy that into that buffer that our colleague set up with just 32 bits of space for the TIMZ. And this results in a heap overflow in this stack and on other stacks as well. It's somewhat tricky to exploit this in a stable way because, yeah, I think mostly because I'm lacking a debugger at the moment, like a decent debugger. Also, the older iPhones have a Nucleus real-time operating system, and then the newer ones have switched to ThreadX. So this means that you have a slightly different heap implementation, which is annoying. But I mean, it means that you have to write two different exploits.
Short remark, we have 5 minutes left, but when the audience,
okay.
we can continue 5 to 10 minutes
okay.
into the lunch break, okay?
Okay. So I think, I'll speed up a little bit. So there's another example in the Qualcomm code base, which is of a similar quality. Again, a length field that is for a fixed length thing, namely a challenge response authentication is used in UMTS. This is called the auth-end challenge, not the RAND that you know from GSM, but it's a new thing, and also it always is 128 bits. Again, there's a length field. And on Qualcomm stacks, this allows you to overwrite the stack. And this is actually easier to exploit than the bug in the Infineon stacks. And again, just as the other one, this allows you to have remote code execution on the baseband processor before any authentication has happened. And this has been fixed by Qualcomm, as I understand it, and it has been pushed to the OEMs, but I haven't seen any images that have been distributed to the customers yet that actually fix this. And the scary thing about this is that it's like, this is, I think, less than 100 bytes. If I'm not mistaken, it's like a 73-byte layer 3 message that you can send over the air, and you have code execution, and I'll show you what you can do with that. I think I should skip through this, because what can we do that's interesting? So we don't want to do much work because we already spent a lot of time reversing. So there is, I always surprised when I found this. Like, I've seen this in the days of when I used a modem. So there used to be this highest command set for modems. And there's a thing, AT plus a 0 equals the number of rings for turning on auto answer. And this is present in some stacks, notably in Infineon and Qualcomm. You can enable and disable this on iPhones using this combination, which is not documented. But the thing is, there's code there to turn this on, right? So it just, if you jump into this routine that does into this handler for this AT command with the R0 register set to the number of rings, then you have turned it on. Now, in Infineon stacks, doesn't matter what you do thereafter. You can just like crash the baseband because it's written to NVRAM. In Qualcomm stacks, you have to make sure that you actually like progress in the logical execution because it's just in RAM. So if you crash, it's gone. Like, doesn't come back. And this is like an excellent target to demonstrate many of these memory corruptions. And with a little more work, you can also make the auto answer invisible by basically making sure that the ring is never reaching the other side. So there's like a ring that is basically a ring string that is sent to the application processor if it's like this text-based communication. And if you just suppress this, then nobody will know and the phone will just pick up. Practicality. So new base stations were expensive. Okay, so the cheapest actually was 25, not 50K. But old gear is often sold on eBay. And hardware has become cheap. We've seen that, and we have two open source solutions at the moment, namely OpenBSC and OpenBTS. OpenBTS provided service during Burning Man, and OpenBSC was tested at HAR 2009 very successfully. I was a subscriber as well then. So this was one of the, oh, this is very dark. I think we should skip that. This was the BS11. Some of you may have seen that. That was one of the first things that was used with OpenBTC. These are the IP access nano BTSs. So these are somewhat pricey, 4,500. The OpenBTS was cheap but very heavy, so it had to lug around 48 kilograms for 250 euros. Here you have something that's just, I think, a kilo, and that's 4,500. There's something in between that I've used and broken, apparently. So the price for this is approximately $1,250 plus a good clock. And this is like a software-defined radio, the USRP. It's very versatile. You can not just do attacks on GSM with it. We've also done DECT research with it. You can also do RFID sniffing with it and many other things. You can watch TV with it if you want to. So yes, there is no layer 1 for GPRS, but it's a nice, like, OpenBTS is very, very easy to modify, and that's why I chose it as a target. And like, this is easier to drag around than this BS11 and cheaper than the IP access nano BTS. Now, the demo, I'll set this up. Common failures. I flagged clock precision oftentimes because I used the stock clock initially, but also because I had I have a fuzzy one in this, like an external clock. It's somewhat imprecise still. Even if you tune it, it drifts within the length of this talk, so that like an iPhone 4 will not hook onto the base station. But there are better solutions. For instance, there are a couple of Russian guys who produce something called the clock tamer, and I've used one of these when I was in the US recently, and they are very, very good. Like, they give good stability. And I'm waiting for my module here. The other thing I often ran into was that I misinterpreted the stack traces because you basically overwrite too much. And the same thing is, like, you can, it's easy to trigger the wrong bug because there may be more than one in a function. And last but not least, I also overlooked sometimes that code was placed on not an executable page. That's why I said it's useful to dump the MMU configuration before you get serious about this. We'll skip this and talk about the baseband apocalypse. So why I really care about this is because you can do really nasty shit. I mean, consider you do this attack in a crowded and or sensitive area, like in an airport lounge, in a financial district, like Luxembourg, near embassies, high-volley targets again. Now, you have some more budget to spend on developing exploits, so you don't like this stupid auto-answer thing that's like ridiculous. So you just record audio, compress it, and like, there's lots of RAM there. Store it in RAM, piggyback onto the next data connection, and just send it out, because the baseband controls the microphone. The application CPU cannot disconnect the microphone usually. And in lots of the newer chipsets, also the camera hangs off there. So you can have fun, depending on who you are. And if you have a shared memory architecture, then you can compromise the application CPU as well, which is very bad, because then all of the hardening features that you've built into the operating system on the application CPU, they're basically useless, because the attacker just uses a different vector. Something I haven't done, because it's difficult to do legally, is looked into ping pong games. If you have access to the base transceiver stations that are used by mobile operators as well, then you can probably find similar bugs in the software running there if you look long enough. And then you can just like compromise the cell phone, and then you fingerprint the other side, like what kind of BTS do I have? Then you compromise that, and you infect more phones. This is like a 2-year project, though, I think, if you have a team of like 5 to 6 people who are serious about this. You can brick phones permanently. I've done that accidentally. 2 Nokias died. Yeah, I mean, you can do this intentionally. For me, it was unintentionally. And the other problem is there's no easy forensics possible here. If you're smart, you make sure that you don't write anything to flash. It all stays in RAM, and at the next power off, everything's gone. And I mean, the privacy problems were one thing, but you can also, I mean, of course, you can also do billing problems for the carrier by sending out SMSs or doing premium voice calls. And it doesn't have to happen at the time that you compromise the phone. You just do it like a random time interval, like 5 to 7 hours later, and it'll be somewhat tricky to figure out what was the original problem and why all of these people suddenly send premium text to this one number. And this is also something that gets you around most of the fraud detection if you do many, many small transactions. So it's an arms race. To do forensics, you need exploits again because they've disabled JTAG on most of the phones. So the scary bit is that at the moment, I don't really know how we can defend ourselves. I mean, we turn off all our cell phones. I don't think that's a solution. It's like, with these things, it's kind of hard as well. How do you know that it's off? It's like a software animation that shows me the slider. Hell, I don't know. Could be on still. So there's this funny story about some German company that apparently produces secure end-to-end solutions for governments. And they have this enclosure, this soundproof enclosure now for the phones because they only trust the headsets. This tells you something about the potential problems that they have in the firmware of the phone that they're using. But I think there still is hope for the paranoid, and you probably have seen the talk by Harald, and I think this is a project that we should all support because if we have an open source and or free software GSM baseband stack, then more people can actually look at the source code and will hopefully look at the source code of that and shake out security bugs. And Osmocom, as I gathered from the information publicly available, implements layer 1 to 3. Correct me if this is wrong. Targets Calypso, and I think recently people have started working on MTK as well. And the Calypso chipsets that you can use are present in the OpenMoco and in the Motorola, the cheap Motorola phones. And the current functionality is about GSM phase 1 from what I've seen. So you can send and receive SMS, and you can have voice calls. So let's talk about disclosure. Qualcomm, I had really strong feelings about disclosure initially, but Qualcomm has been fantastic. It was great working together. Apple was a little bit slower, but they fixed this TIMSY bug this week as well, and they will get more bugs to fix. Same for Qualcomm. There was a vendor outreach program by Microsoft who basically contacted all of the baseband vendors, if I understand this process correctly. And one interesting remark I got from someone from Sony Ericsson, ST Ericsson, who explicitly told me that he can publish this email, so I use parts of this email. Now, I'd like to do that because it shows that there's a certain disconnect between people who do this engineering and the people who do vulnerability development. So he thinks that stack canaries that are checked in the scheduler prevent problems with stack overflows. Not quite. This helps if your engineering department shoots itself in the foot with an accidental stack overflow. It doesn't help against an attacker who does this maliciously. And using Coverity on the real-time operating system, well, yeah, they might have done that, but it still found bugs there. So, and plenty of them. So, I think there's a need to educate the engineers who develop these, not just cell phones, but embedded systems, software in general, to be more careful and take security into account as well. And the outlook is that we will see the same problems again for UMTS 3GPP, and you say, well, okay, so 3GPP uses mutual authentication, so it will only be the very well-funded adversaries who can get past that, who can do all these attacks. But it turns out that there's this humongous radio resource control layer, which is like 1,800 pages of specification encoded in ASN1 PER, and there's only one single vendor that I've seen in terms of parses in the baseband stacks. And I think within the next 1 or 2 years, we'll see femtocells as very cheap attack platforms. Thankfully, the LTE specification that's used the part that uses pre-authentication is simpler than 3GPP, so there may still be hope there. But for now, I mean, if we have to live with 3GPP at the moment, like this attack platform costs 40 to 60 pounds on eBay, Great Britain, and there's still a significant amount of work to repurpose it, but I think it's possible. And with this, I'd like to finish. So memory corruptions over the air interface are possible, even with cheap hardware. Cheap, well, okay, below $2,000. Vulnerability, I mean, it's a price of a halfway decent laptop, right? So you shouldn't discount that. Vulnerabilities in the GSM baseband code bases are plentiful at the moment. I hope that'll change. It plays into the hand of the attackers that there's only a relatively small number of baseband vendors. And well, if you have malicious code execution on the baseband CPU, then you can do a lot of really funny things. And if you have this shared memory design, you can compromise security completely. So that's been it for the non-demo part. I'd like to thank the University of Luxembourg for supporting me. I'd like to very much thank the anonymous engineer for bringing my attention to this. And I think it was, yeah, Jacob Applebaum was the one who brought me in contact with him. Dynamics basically sponsored the tools for this. Harald Welte helped me out technically a couple of times. Sylvain has been very great today with the used RP that failed. André Stempe helped me with soldering things back in Luxembourg, and Carsten Knoll and Harald thankfully provided me. Well, no, sorry, I'm thankful for them providing me with replacement gear because of my failed USRP, and of course Cashel for writing OpenBTS, and Qualcomm and Apple, last but not least, for fixing all these bugs. And I'm really serious about this. Thank you, because there are other industries I've seen recently in embedded systems where people care a little bit less. So, yes.